Okay, we're going to look at synthetic routes now. So at A level, what you've got to be able to do is you've got to be able to say how you convert one molecule into another for up to 4 different steps. Now, before we can even start synthetic routes, it's really important that you know the reactions of all of your functional groups. So whether that be any of these, so if you don't know all of your reactions, that's all of your agents and conditions and all of your mechanisms, then don't start this section. So the first thing that we're going to do when we're working out a synthetic route is to work out a scheme. Now, we do that by starting to write down the formula of the starting material. So for example, if the starting material was molecule A and we wanted to make molecule X, which we would call the target molecule. I want to get from there to there. And we're asked how we're going to do that. This is the technique that you should use. What we should do first is we should work out all of the compounds which can be made from this starting material. So let's say it can make B, we can make A into C, into D, and then to E. Okay. So just write them all down. And then do the same thing for X. Let's just think about how we can make X. So write down all the different ways that we can make X. Let's say we can make T into X, U into X, V into X, and W into X. So we know we can make A into B, C, D, and E. And to make X, we can use T, U, V, or W. Now let's say this is a 3-step synthesis. So it's going to take 3 steps. One of these would be the first step, and one of these would be the third step. What we're then going to do is work out what the second step is. So I would look at the structures of these molecules here and the structures of those molecules there. And if we can make one of those molecules into one of those molecules, we've got our synthesis. For example, if we know we can make B into V, like this, then our reaction scheme would be start with A, make B, and then make V, which would make X, our target molecule, via these 3 steps. And then we'd answer the question like that. Now it's important to keep the number of steps as small as possible to maximise the yield of the target. Sometimes you see straight away that a particular reaction will be needed. So for example, if the target molecule here had 1 more carbon than the atom in the start material, it's likely that the reaction will involve cyanide ions with a haloalkane, because it's the reaction of a cyanide ion with a haloalkane that increases the length of the carbon chain by 1. For example, if our start material here is bromomethane and we want to extend the carbon chain, then the chances are it's going to involve a cyanide ion. So as a general rule in A-level chemistry, if you are increasing the carbon chain, here's from 1 carbon to 2 carbons, then that will always involve a Cn minus. That is a very handy exam hint. Okay, and that is always a Cn minus ion reacting with a halo alkane to produce a nitrile. Okay, what we need to do is we need to revise how all the functional groups are connected, and that's what we're going to do now. Okay, what you need to do now is you need to get a large piece of paper, at least A4, preferably A3 if you've got a piece of A3 paper. And what we're going to do is we're going to write down all the reaction schemes that connect all of these groups together. Now all I'm going to do is I'm just going to draw the outline of this, and it's up to you to write the information on top of the arrows. If you get good at this, you should be able to do this from memory. Right, what I suggest you do is you take a note of this and you make lots and lots of copies of this reaction scheme just like this, and then from memory you need to train yourself to identify how you convert one thing into another. So for example, I know that an acid chloride can make an ester. I know that we can turn an ester into alcohol. I know that we can turn alcohol back into an ester. We know how to turn an alcohol to a ketone, and we know how to reduce a ketone back into an alcohol. So these are all of the conversions that you need to know about. And all of these have been covered at some point, whether that be last year in year 12 or this year in year 13. Okay, so you can see here there are 1, 2, 3, 4, 5 different ways to make a carboxylic acid. 3 ways to make an ester. Only 1 way to make an aldehyde. 2 ways to make an amine. 1 way to make an alkane, etc. So please learn how you do all of this, how you actually do these, so you're able to do this. Okay, let's have a look at some detail now. Let's have a look and recap some reagents. The first group of reagents we're going to look at is oxidizing agents. So this is potassium dichromate 6 acidified with dilute sulfuric acid. And we know that they will oxidize primary alcohols to aldehydes, and aldehydes further to carboxylic acids, and secondary alcohols to ketones, and we know that tertiary alcohols cannot be oxidized. So there's our first reagents that we're going to look at. We know that there are reducing agents as well. And we have different reducing agents. So one reducing agent that we learn is this molecule here. Now that molecule there's got a long name, but we just remember this. It's sodium tetrahydroborate 3. So that's sodium tetrahydroborate 3, and the Roman numeral 3 is the oxidation state on the boron here. Tetrahydrido, that's because there's 4 H- ions in there. Now this substance here will reduce CO but will not reduce CC double bond. And the reason why it will reduce this CO here is because this bond here is polar. So this is delta positive and that is delta negative. So the lone pair on the hydride ion is attracted to that positive carbon there. Get that curly arrow there, don't we? It will not reduce the CC double bond, and that is because this CC's bond here is electron rich, and the lone pair here, because it's electron rich, that would repel. So it would repel, so there'd be no reaction. Our second reducing agent that we're going to recap here is hydrogen with a nickel catalyst. Now, hydrogen and nickel catalyst is used to reduce CC, but not CO. Okay, so if you're going to reduce a carbonyl, you need this. If you want to reduce a carbon-carbon double bond, you need that. Now, fourth reducing agent is tin, which is the symbol SN, and hydrochloric acid. Now, tin hydrochloric acid is used to reduce that to that. And usually this R group here is a benzene ring. So they are the only three reducing agents that you need to know for the exam. We also have dehydrating agents. Now, dehydrating agents are reagents which remove water. So, for example, if we want to turn an alcohol into an alkene, we can use a dehydrating agent. And what you would do is you would pass the vapour of alcohol over heated aluminium oxide. Or we could use an acid catalyzed elimination reaction. Please look back at year 12 to write down how you would do that. And that would produce an alkene plus a molecule of water, because that's what dehydration is. Okay, let's now have a look at some reaction schemes. Let's ask ourselves the question, how can propanoic acid be synthesized from 1-bromopropane? So what have I got here? I've got 1-bromopropane, and I want to make propanoic acid. Both the start material and the target here have the same number of carbon atoms, so no alteration of the carbon skeleton is needed. Therefore, I'm not going to need Cr-, that's definite. That's the first thing I'm going to look at. So whether I'm going to increase the carbon chain, because if that's the case, I would need Cn-. So the first thing we need to do is to write down all the compounds which can be made using just one step from 1-bromopropane. So let's do that. So I know I can make 4 different things from 1-bromopropane. So it's going to have to start with one of those 4. The next thing we need to do is to write down the same thing, but everything that would produce propanoic acid. Okay, so 1-bromopropane here can be converted into propan-1-ol, which can be converted to propanoic acid. So we can see here there's propan-1-ol there and propan-1-ol there. Therefore, we know that this can just be done in 2 steps. So from 1-bromopropane to propan-1-ol to propanoic acid. So let's have a look at the steps. So we'll call this step 1. We'll call that one step 2. So if we reflux that with sodium hydroxide, the OH minus there will act as a nucleophile, and the haloalkane we know will turn into an alcohol. Now, if you didn't know that, you need to go back to the haloalkanes topic that we did last year. And the propan-1-ol can be oxidized to propanoic acid. Using these conditions here and reagents. So there's an example of a two-step synthesis. Let's have a look at another one now. Let's have a look at a three-step one. So how can propylamine be synthesized from ethene? So the first thing to note here is that propylamine has one more carbon than ethene. So this suggests the formation of a nitrile is involved at some stage. So we're going to need some Cr- at some point, and the intermediate, or one of the intermediate, is going to be a nitrile. That's because we're increasing the carbon chain. That's my first little tip there. So, just like we did in the previous example, we need to write down all the compounds that can be made from ethene and all the compounds from which the propylamine here can be made. So we know that alkenes can be made into alcohols, haloalkanes and dihaloalkanes. And we know if we want to make an amine, we can use an amide, a nitrile, or haloalkane. So in this instance, no compound that can be made from one step, from the start material, appears here. So it can't be converted directly it can't be converted from in two steps. So I'm going to need three steps. So we already know that the formation of a nitrile is required. So a haloalkane can be converted to propane nitrile. So the synthesis can be completed in 3 steps. So we know that a propane nitrile, or nitrile in this case, is made from a haloalkane. So there's my 3 steps there. 1, 2, 3. Let's have a look at the 3 steps in a bit more detail. There we are, there's the 3 steps there. HBr on the first step, KCN in dilute sulfuric acid in the second, and hydrogen and nickel catalyst in the third. So I put haloalkane, EG, bromomethane. So chloroethane or iodoethane could have also been chosen instead of bromoethane. Instead, I would just put HCl or HIA instead of HBr. That would have been okay. Okay, now we're going to have a look at an aromatic reaction now, or a few of those. So what I'm going to do now is I'm going to draw a diagram which summarises aromatic reactions. So when I write benzene here, that could summarise anything which contains a benzene ring. You've got to know that one. And this one here. Just make sure that you can recall the reagents and conditions for each of these 3 conversions as well, with a benzene ring as a start material.